So today's lecture is about radar detection of shallow weather phenomena, and I'm very happy to do this topic because it talks about some of the limits of weather radar, and these are always the things that are quite embarrassing to weather radar scientists or to the Weather Service. And what I'd like to do is to talk about that today and explain what the issues are. So this is much about the radar instrument, which when you become experts, you need to know what the limitations of your instruments, and this is one of the objectives of this presentation. But I choose to use shallow weather to illustrate that. So let me just get rid of some of my windows for just a second. Okay, so the objective, as I just mentioned, was to talk about the weather radar and from quite a radar perspective. When we get into the classroom, we'll explore this more in terms of interpretation, which we briefly get into here, but we'll get into it more during the classroom. Okay, so I'm going to start by discussing some examples of what I mean. And then we're going to do some what we call calculations, typical reflectivities, talk about the beam height, the beam width, the sensitivities. This is all radar related, about the performance of your radar, but it has an impact on how you interpret the images. And so we'll be looking at drizzle, talk about lake effect snow, clear air echoes, or graphic precipitation. That's where these issues of sensitivity, beam height, and play a role. Okay, so when I talk about low-level phenomena, these are the letters in blue are the things I talk about that are meteorological. So often drizzle is very shallow; it's very light. Raining, you often see weather radar images like the one on the right, but what you really don't know is what's happening on the ground, because those echoes, those images are maybe made, depending on how far you are from the radar, a kilometer, 2 or 3 kilometers above the ground. And below that, it could be evaporating, or it could be even getting heavier. So when we talk about rain, snow, or hail, that's what we're referring to. Some of the non-meteorological targets that are very important for nowcasting are things like lake breezes, convergence lines, gust fronts. Those three things are not really, don't have a precipitation signal per se, but they can be detected by weather radar because they can see them through insects. And we can talk about that more. But insects are actually very good scatterers. You don't need very many insects in a cubic meter for the weather radar to see it. And insects get carried by the wind. So when you have a lake breeze and you have a convergence zone, the insects, the winds bring the insects all together, and so you can actually begin to see them quite well. So this applies to lake breezes, convergence line, gust fronts. Things like microburst tornadoes in cold pools or the cold air from thunderstorms are not meteorological, are often below the height of that the radar is looking at. And so it's really difficult to see these features. Tornadoes generally are below cloud base, and if your radar is above cloud base, looking at it above cloud base, you can't see those. Same with microbursts and cold pools. And these are important for nowcasters. Other things, and I'm not going to discuss in the black, that you see at low levels and not at high levels, are things like insects, birds, and bats, as I've already mentioned, but also other things like interference due to radio local area networks, the sun, something we call second trip echoes. You only see at the low elevation angles, not at the high, because the second trip at high elevation angle, there is no echo up there because you're looking so high. You only see them low down. We'll talk about that in the non-meteorological radar section. Other things that you don't see Up high, but you see at a low level, are things like buildings, mountains, forests, and various ground clutter. And the other things that you don't see are things like airplanes. Well, airplanes you'll see, but things like cars you see at low levels, ships, debris you can see. When I talk about space debris, I was referring to there was a couple explosions of the NASA space shuttles, and you tended to see them at low levels rather than high levels. Other things that we're not going to talk about here are forest fires and sea clutter. So there's lots of things you can see, but just in the interest of time, we'll just keep going here. We can talk about it during the classroom sessions. So, so I was trying to make some general comments about what happens when low-level scanning versus high-level scanning. Things that you really want to do when you want your radar to scan at low levels. And trying to figure out what the requirements for that low-level scanning is. Well, there's a wide variety of phenomena. You can see things from hail to drizzle. And so you really need quite a large, your radar needs to have quite a large, be able to measure a large range of values, what we call dynamic range. And it can go from values of minus 30 dBz, which is turbulence and drizzle and fog, to hail. Hail tends to be around 60 dBz, and you can even get higher, up to, I've seen up to 95 dBz worth of echo due to shifts. Other things about low-level scanning, in terms of Doppler. What is anything special about Doppler? Not really. I think a lot of the targets that we're looking at low level have zero velocity, like ground clutter, and so you can actually filter them out. But even then, you have typhoons, which you can see with large velocities. So there's really nothing special about Doppler that we have to worry about. Now, what about other advanced uses of weather radars? Some of the advanced uses is something called a variational Doppler radar assimilation system. What this does is it takes the Doppler radar data, assimilates it into a numerical weather prediction model, and then it's able to retrieve temperature, humidity, things like that. And from that, you can derive something like cold pools. So, so you do want to do low-level scannings to be able to capture those cold pools as best as you can, but you need, you know, sophisticated processing systems. Another thing that's really good for low-level scanning is ground clutter. Ground clutter is a negative, but it's also a very positive thing, in the sense that if you see ground clutter in dry conditions and you compare it to ground clutter in wet conditions, and you're able to determine how the path of the radar beam changes between the wet and the dry conditions, you can actually retrieve the humidity. So there are some very advanced uses in research, but they're not very common in operations just yet. But you will. These are some of the things that I think you will see in the next 10 years. One of the commonalities of all of these things is that when you look at low-level phenomena, there's limited range. You don't see things very far out. And it's because of the beam propagation. Some of the things that we'll be looking at are very low echo strength, and that's when you don't see things. And generally, the radar sensitivity becomes a critical issue. So these are just my reflections before I even started preparing this. So let's get into the examples. So Drizzle, some radar examples. Here's an example from Germany. And I hope you can see my pencil here. And you can see this is an inset of this area down here. This is from Germany. This is using the Nino system. So reported in the surface observations is this, or these symbols, and that indicates drizzle. But the radar doesn't see it very well. Okay, so this is just a starting point here. Okay, let me just move my window out of the way. Okay, and I think you'll be using Nino during the classroom session. It's a very flexible system. Just to give you an idea of what it can do, it takes in the radar data, and then it visualizes the data, color codes it in different ways. And so the raw data goes in, but the representation of it is, is done here. And for example, you have 256 radar values, and it goes into 7 values here, for example. So you have control over that. So let me go to the next slide. So here's another example. Again, here's the image that we're looking at, and there's some drizzle in here. Again, not very many echoes being observed. I'm going to show you another image. This one is from Finland. So here's quite a different image. Now you have range rings here. The maximum range here is 250 kilometers. So you're seeing this green echo, which is around anywhere from 0 to about minus 10 dBz, maybe even some minus 20s in there. So this is an example of drizzle. And so the question is, why was drizzle observed in Finland so well, but not in Germany? And another question is, why is the drizzle observed only around the radar and not farther out? Let's just get the pen going here for a second. And why is the drizzle stronger in this area near the radar versus this area, which is farther away from the radar? So there's a drop off in terms of the radar echo with range. So the question is, why is there a range limit to see the drizzle? Okay, wrong way, sorry. So let's talk about minimum detectable signal. So we're going to try to answer those questions. Okay, so here is a graph, and I'm going to try to define what I mean by minimum detectable signal. Here's the range away from the radar. Just imagine that you took some radar data, and you plotted all the data around a ring, which represents constant range, and you just created a PDF, a probability distribution function of the data. So in this, it will change with every piece of data you have. So in this case, so at 50 kilometers, for example, the peak is around 25 dBz. So you might have more rain, and the pattern would look different. The thing I'm concerned about is what I'm looking at the bottom graph at the bottom line. So the colors really aren't important here. It's a function of the weather. But I'm more concerned about this. This is the line that defines the minimum detectable signal. And we'll explain why. We can ask the question, why is it this shape? Why does it look like this curved shape here? And it's because when I talk about minimum detectable signal, we're talking about power, right? The power, the minimum, it doesn't matter how far it is, but when we convert it to reflectivity, dBz, it becomes this curve because of the 1 over r squared in the radar equation. We can talk about that more during the class. So that's the radar equation. And so when radar people talk to each other, we ask what is the sensitivity of your radar? Because that's one of the markers of how good your radar is. So we ask, it can be described as the noise temperature of your radar receiver. But for radar people, we typically like to talk about reflectivity at a certain range. As you can see, it's a function of range. So we just pick a range, and 50 kilometers is a good range. It could be 100, it could be 1 kilometer range. But we generally like to pick a number like 50 kilometers because that's where the radar seems to work the best. So typically in this case, the sensitivity of this particular radar is about 1 dBz at 50 kilometers. So that's what I mean by minimum detectable signal. Okay, let's change graph. So here's the radar equation. Here's power. Here's the radar constant. Here's reflectivity in units of millimeters to the sixth to the meters to the cube. And I call that the linear reflectivity factor because power is proportional to Z in a linear way. But we often talk about dBz, units of dBz, where it's 10 log of this number. Okay, so Z is equal to ND to the sixth, and we often take that, take the log of it, multiply by 10, and call it decibel, units of decibels, just because of the large dynamic range. Okay. So just to repeat what I just said, the radar measures power, and there's a minimum power that the receiver can detect. So that defines what the reflectivity minimum is. So the radar equation converts power to Z, and so we can compute what this value is, and you will be doing that in your homework. So my statement, my fourth bullet here is to say that at long range, detection of weak echoes is limited by the radar sensitivity. If the reflectivity of the target, your drizzle, is below the MDS, then the radar doesn't see it. Okay? Now, one of the points I'm going to make is beware of the artificial MDS, where it's not a function of the radar, but it's a function of the display. And I'll point that out in a second. So in the homework questions, I ask you to calculate, give me a typical size of some drizzle, typical average intensity. I ask you to calculate the number of particles per cubic meter, calculate what it is in Z, then calculate what it is in dBz. And this is part of your homework questions. But just to go back to remind you, Z, the relationship between Z and the number of particles and the size is Z is equal to this number times this number to the sixth power, and get the units right. This is in meters per cube, this is in millimeters. Okay, so I go back and ask the question, can your radar see drizzle of a reflectivity of, say, -5 dBz? So in this case, it's -11, but I'm asking the question, can you see, say, a 5 dBz? Okay, so going the wrong way. So let's go back to this graph. So if your radar had a sensitivity of -5 dBz, and I draw this curve here, what this says is that if your drizzle is lower than 5 dBz, then you should be able to see, if this is your radar and your drizzle is -5 dBz, then you should be able to see that echo all the way up to about 25-kilometer range. So what if your radar is set at 7 dBz? If you have created an artificial situation where your display system is limiting what you see. As what I was trying to point out with Nino, you have a flexibility of what you see or you can't see by setting it in the display system. What if it's 7 dBz? And what it says is all that data in that shaded area you can't see. So look at the value here, the yellow side, yellow box, which is this is the lowest echo that you can see in this display, and it's set at 7 dBz. So if there is any drizzle less than 7 dBz, it's thresholded out, and you can't see it. So you have to be careful that even though your radar may be able to see it, you have to be careful that your display doesn't is set to be able to see it. So one of the reasons why the radar is here, it can't see this drizzle is probably because it's thresholded out. Okay. So one of the questions that you should ask yourself is, what is your sensitivity of your radar? Here are different curves of that, the minimum curve, 1/r² curve of reflectivity versus range. And and the question that you should try to find out is, where does your radar fit on this diagram? And the people that would really know this question is your radar engineers. And so, and a typical radar is anywhere from about, at 50-kilometer range, this is about 50 to minus 10 to minus 15. The lower the value, the more you can see. So this is where you need to know something about your radar. Okay, let's shift gears a little bit and talk about beam height considerations. This is a graph that I often refer to as radar person. And here is range again. And here is height above the surface of the Earth. And here are different elevation angles, 0.5, 1, 2 degrees. We'll focus on the 0.5 degree elevation angle. You can see that this curve gets higher and higher the farther you get from the radar. So at 200 kilometers, a 0.5 degree beam, just skimming the Earth's surface, is actually 4 kilometers above the ground. So one question you should ask, again, your radar engineers in your system, is if you have weather that's only a kilometer or 2 kilometers in height. You know, here's 2 kilometers here. Let me see if I can draw this. I'm trying to use the pen here. And if you are 2 kilometers in height, your weather is 2 kilometers in height, your beam is overshooting your weather. And so if, say, your drizzle is only like half a kilometer above the ground, say around this area, you don't see it very high. So there's 2 competing factors here. Minimum detectable signal and in height of the beam. So let's define some terminology so we get it clear. When I say detection, when we use the word detection in the radar business, it means we can detect it, we can see it. We not necessarily get the right value quantitatively, but we can actually know it's there. When we talk about a measurement, we know we can get the value correct, right? So here is a 1 degree beam. The orange line represents the top of the beam. This orange line at the bottom, let me get the pen again. So this is the bottom of the beam. This is the top of a 1 degree beam. Again, a function of range, function of height. So this is a 1 degree beam of a radar. Look at 250 kilometers. Look how this is the width of the beam. So 1, 2, 4, almost, it's more than 2 kilometers deep. Okay. So, and the dotted line represents this middle of the beam. Okay. So if you have shallow weather that's a kilometer deep, oh, lost the pen again. It's only a kilometer deep here. Come on, yep, here. Then the radar overshoots, totally overshoots the weather at about 125 kilometers. Here's another point closer in. At this point, the top of the beam begins to overshoot the weather. Okay, so at this distance, we see nothing. At this distance, we begin to see the beam is not filled with the weather. So at that point, we're not really measuring accurately we're not measuring the weather accurately enough. We're detecting it. So this is what we mean by that. So we mean at this point that the beam in the detection area, we say that the beam is only partially filled. Okay, so we will use that terminology. Okay. So let's go back to this question. Drizzle, and just pointing out a side issue here. Here's a zoom up of some of that previous data. That's a little bit different case. You can see the drop off drop off with range of the reflectivity echo. This is what we mean. Here we're detecting it well quantitatively. We're measuring it well. Here we're starting to lose it due to beam filling issues. Okay, and here is an example of how high the weather is. These are vertical cross sections. So this is range along the x-axis and height along the vertical axis. And what it shows is that the height of the drizzle is only about a kilometer, 1.25 kilometers above the surface. So it's like that example in the previous case that only when you're close to the radar, look at the distances that you can see accurately the weather, you can measure it well. Here you're starting to drop off with range. Okay. Just to add some polarization signature is here's the ZDR, and I think you've taken enough of the ZDR to know that values around 0 means that the particles are round. So so this is the ZDR signature. So and look at the values of the reflectivity. They're around -5, maybe even brighter to up to 0. So this is fairly large particles of that's shown up here. Okay. So one of the major differences would be it could be thresholded. Why is drizzle observed only around the radar? It's a sensitivity issue of the radar. So if the radar is a sensitive radar, you can begin to see it. This is not to say that the German radar is poor in terms of its sensitivity. It's just that it may be thresholded. And so why is the reflectivity pattern stronger near the radar and decreases away from the radar? The answer is because it's the beam's starting to be not filled. So, and why there is a range limit, and again, it's because of the beam filling, the depth of the drizzle, and to some extent due to sensitivity. So these are kind of bread and butter to the situation. So here is an example of again more drizzle in the German display system, and you notice that it's starting to show a loft. These are the map. These are the vertical cross sections, and you can start seeing that some of the materials are loft. And notice that they're starting to lower the thresholds to see more and more of that drizzle. I think if they even lower it even more, they probably see even more. Okay, so this is really a repeat of what I've been saying, and as a radar person, I keep going back to these 4 bullets. And in the past, I asked everybody to select the most significant issue for your particular radar, and it's a kind of a trick question in that they are all important. Okay, we're kind of coming to the about 3/4 of the way through the presentation. So I wanted to talk about other issues about fog. You know, often the question is, it's really heavy, dense fog, and can the radar see fog? Well, part of the homework question is for you to kind of work that out. And I'll sort of give you the answer ahead of time, but I'm asking you to do some calculations to convince yourself that why fog is such a difficult thing. So in this case, this is a radar from Japan. It's a special radar. It's not an operational radar. It's not, your radars are S-band, which is 10 centimeter wavelengths, C-band, which is 5, X-band, which is 3. This is a 1 centimeter wavelength radar, specially designed to measure fog. So look at the distances. The distances are only, this is only 10 kilometers from the radar, from edge to edge. So it's only seeing it very close to the radar. But look at some of the values that are being displayed. Minus 12 down to the blues, which goes to about minus 30. So the reflectivities are quite small, and it's because the fogs are quite small. So the reflectivities are quite small. So the homework question is for you to calculate, put some sample numbers in it and work out what the values you think are. And here's just, I thought you might be interested in seeing, here's range on the bottom of the axis on the side. Again, I'll try to use the pen. So what I'm talking, here's range from the radar in both cases. In height, these are in meters. So this is height in meters. And so fog is very shallow, 500 meters. Oops. Only about 500 meters above the ground. So very shallow. Here we have Doppler, and this is reflectivity. But just focus on the reflectivity. You can see how weak it is. So one of the immediate questions is, why don't we see fog? Because the sensitivity of the radars generally I should say the reflectivity of the fog is much lower than the sensitivity of our radars. We might be able to see it very close to the radar, but generally an operational radar has a really good operational radar has a sensitivity of about minus 8 to minus 11 at 50 kilometers, and where minus 12 and minus 30 is really quite low. So I ask you to estimate those numbers in your homework. Okay, let's go back to beam height and beam filling again and talk about quantitative measurements. So supposing we have a virga situation, and this box represents virga. Virga meaning it's raining up aloft, but it evaporates on the way down. So we don't have any echo below this box, but we have echo above it, in this box. So the interesting thing is in this area where the beam is not completely filled, this particular beam is not completely filled, we start getting poor estimates. We can only detect it well. So the only place where we can measure it well is actually in this shaded box. Okay, so again, it's and the way to overcome this, well, for close in, well, we can do multiple elevation angles, right? And we can build a product using the beams that we think are filled versus beams that aren't filled. So there's a lot of processing to radar data to try to compensate for these physical effects. Nothing wrong with the radar. They're just physical effects of what the beam and how your radar works. Okay, another reason what happens is to explain what happens in shallow weather. Here's an example of what we call a vertical profile of reflectivity. So range, the horizontal axis here is range, the vertical axis is height, and this black solid polygon near zero velocity is a theoretical profile of snow with some bright banding here, with the extra tail here. So what I've done is take this profile and estimated what the profile would look like at 50 kilometers, at 100 kilometers, 150, 200, and 250 kilometers, due purely to the beam width, smoothing of the data. So as you recall, at 250 or 300 kilometers from the radar, the beam width is about 4 kilometers deep. So it is smoothing this profile considerably. So the question is, what happens to your reflectivity when that happens? And this is what happens. These numbers represent, say this is the true value that you want, and this is the bright band. If you had this profile at 0 kilometer range and you move it to 50 kilometer range, this is what it would look like. And if you move it to 200 kilometers range, this is what it would look like. It would only measure 28% of this value here, the maximum value. Let me use the pen again. The maximum value here is 28% of this value here. So this is what this vertical profile effect is a function of the beam getting wider and wider and wider and smoothing the data out. Okay. And here's an example from Finland. Here's an example almost identical from 0 to 100 kilometers. And this is a shallow snow system where you've got more intensity falls off with height. This is height on this axis, and this is 2 kilometers. And you can see that as the beam goes wider and wider out, it smooths the data. So this is not the beam. This area. This is a series of beams creating this image. So this is the top of the sequence, which I think is about 10 elevation angles. This is the bottom of the sequence, and they're plotting it all together. What it's showing is that as you go away from the radar, the values get lower and lower and lower, and it's because of the beam smoothing effect. Okay. And here's another example of exactly that. So here's a radar in Kuopio in Finland. The radar's at the center here. This is a 1-month accumulation of the precipitation. And it falls off with range. If you look at this, again, here's the center of the radar, and it falls off with range. As the farther you go away from the range, the values get lower and lower and lower. So here's another way of looking at it. You take range along this axis, and what's plotted here is this rain gauge divided by what the radar is looking at. So this value here. So you're dividing, it's presumably the rain gauge, as you go along, is the same everywhere here. And you divide it by by the value that the radar is giving you, and you get this factor. And you see that the gauge divided by the radar is significantly different. And even at this range, 240 kilometer range, this is a 10 log of the value. It's saying that the radar measures 1/100th of what the gauge sees. And that's not due to attenuation, which most people think. It's just due to the fact that you're smoothing the beam. So, and so you can ask the question, what is the effective range of a radar for QPE? We'll talk about this a little bit more next week. But if you look at how flat this area in this region, oops, back with my pen here. The area in this region where it's relatively flat is what we would call the effective range of a radar for quantitative precipitation estimation. Now, the trick that most radar people and processing people, what they do now is try to account for this shape and try to adjust those values for long range. And I want you to point out that, anyway, that I'll move on from here. I'll talk about something in the classroom session. And here's an example from Finland where here's the original composite. And these radars are going out to 250 kilometer range. And look at this area here at the far edges of the radar. Here's another one. And after the profile correction, here's what it starts to fill in. This is of a quasi-stationary front. So this whole area in here was a frontal system, and the precipitation was fairly uniform through here by the gauge analysis. So here's what radar people are doing to adjust the radar data for the beam filling effect. Okay. So here's another issue of shallow weather, and this is one of something I've been focusing on lately. Here's the situation in Switzerland. In Switzerland, it's a mountainous country, so they put all the weather radars on top of mountains. So here's 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 the Pole Valley, but here's the Monte Lima radar. Oops, Monte Lima radar. It's on top of the mountain peak, and here are the elevations that it scans. Here's a different. Here's a cross section through this radar. And what it shows is where they collect the data. This is from Earth Skirming. Very nice graph. But what it's showing is that these radars are on mountaintops because of the elevation angle that they're using, and because if they point it too far down, they get blocked by mountains. You really never see anything in the valleys, right? All the valleys are empty. So, and if you are from a mountainous area, you know that it could be snowing on top and raining at the bottom, and you have no radar data to show for that. Here's another example of how important low-level scanning is. Here's a PPI. This is of radar data. This is reflectivity on this side. And we have echo here and echo here. You can see how you can almost, if you imagine it could be a continuous circle, you might imagine that this looks like this up here. Here's the radial velocity field. We'll talk about that another time. But over here is, I take all the data around a range ring and plot it as a function of height, if reflectivity, and just create probability distributions at every height and at every reflectivity. And so the interesting thing, this is a vertical profile of reflectivity using this data in the middle. And so what has happening here is you can see that the reflectivity increases, then it decreases. Then it increases, and then it decreases, then it increases. What it's telling you is that there are multiple layers of the atmosphere, perhaps 5 layers in this case. And if you're not scanning low enough, you're missing all of that. So this is really a word of caution that, the farther you're out from the radar, and if you're not seeing the low levels, lots of things could be happening below your level of detection. Here's another image. This is what we call a range height indicator, RHI, vertical profile. So this is range. The radar in this case was located in the valley, a very unusual radar. This was done for the Vancouver Olympics. We put a radar in the valley because we considered putting a radar on the peak, but we knew we would be missing. We would not be measuring where all the Olympic events were happening on the slope. So we put a special radar in the valley that would conservatively block. But the message is that if we put a radar on top of the mountain, like if we were putting it up on this peak, see if I can draw it here, or this peak, we would, our radar beam would be like that, and we'd miss where all the precipitation is. The radar, sorry about that, a radar is located here, and this is the radial velocity picture pointing at the mountain. And here's the reflectivity picture pointed at the mountain. These are several elevation angles. So in this case, not the orographic precipitation was not at the peak of the radar, but on the slope of the radar. And it's because the flow is blocked. So we have, when you do Doppler radar, red is usually velocities away from the radar, and blues are velocities toward the radar. Now, you have to be careful in how you interpret it. The way I should have said it is there are components of the wind away from the radar and components of the wind towards the radar. There's flows in and out of the plane of this picture. But the point is that there's flow this way. And what that indicates is that the flow is not flowing over the peak, but it's actually, the airflow is going up and then coming back down. And that's called what we call block flow. And I hope to talk more about that and show you more, explain more of this in our classroom session. So when this happens, the precipitation is not on the peak of the mountaintops, but it's on the slope of the mountaintop. So again, if you put a radar on top of the mountain peaks, you don't see this. And so you have to, as a forecaster, how do you adjust to this? Well, you have to know that these effects can happen, and that you have to interpret what you see aloft in terms of these effects. So if you think you should be seeing things on the peak and you're not, and it's probably because the flow is probably blocked. Here's another example of what you can see at low levels that you can't see at high levels. And this little line of green. If you look at the reflectivities, the green are low reflectivities. The blues and reds are high reflectivities. And this is an example of this convergence line due to insects that we see. So, and what does happen here is at a future date, at a future time, not too much longer, these will be areas of initiation of convection. So you actually do not want to threshold that data, you want to see that. Here's another outflow from a thunderstorm up here that you can see, and that when they begin to meet together, and I've drawn the lines, you start forming explosive growth of convection. Okay. So you want to see lots of low-level stuff. So just in summary, I just wanted to focus on drizzle and some shallow weather to introduce these topics of the limitations of the radar. As users and expert users of radar data, you have to understand the limitations. Because you will be asked about that. So the question is important. And it's very important because the better your instrument can see, the more you can see, the better you have, more tools you have to diagnose severe weather. So there are some things I think that would be useful to you is to find out how the data is processed through your chain. What is the sensitivity? What's the lowest elevation? What's your beam width? How far are your radars apart? Is there a significant gap in between the radars? Those things will help you be a better forecaster.